A silent engine could carry us to the stars. This is the promise of gravity without fuel, where massless drives use the fabric of space for thrust. For centuries, rockets have been chained to their fuel tanks, but new physics is tearing up that old rulebook. By the end of this, you will understand how these impossible engines might actually work and what it means for our future. We will investigate drives that seem to break Newton's laws and ask if a warp bubble is a real possibility. Are you ready to see how far our laws of physics can bend? Isaac Newton's apple did more than just fall. It cemented a law that would chain human ambition to a simple, unyielding truth. For every action, there is an equal and opposite reaction. This principle became the iron rule of motion. To move forward, you must throw something backward. For over 3 centuries, this was the only way. Rockets became magnificent demonstrations of this law, climbing skyward only by hurling immense quantities of burned fuel downward. Their reach was always limited by the sheer mass of the propellant they had to carry. Then came Albert Einstein, who looked at the universe and saw something entirely different. He proposed that gravity is not a mysterious force reaching across space, but a curvature, a warp in the very fabric of spacetime itself, created by mass and energy. This was not just a new equation, it was a new reality. His theory of general relativity introduced mind-bending ideas like gravitational waves rippling across the cosmos. It also opened a tiny, speculative door. If mass could bend spacetime, could we, perhaps, bend it without mass? Could we engineer the fabric of the universe to create motion? Decades later, physicists like Miguel Alcubierre walked through that door. He mathematically described a warp drive, a concept where spacetime itself is manipulated, compressed in front of a spacecraft and expanded behind it. The ship would surf a wave of distorted space, never breaking the cosmic speed limit locally, yet moving faster than light relative to the universe around it. It was a propulsion system with no exhaust, no reaction mass. It was the first serious scientific hint that Newton's cradle might not be the final word. This entire journey from the falling apple to the warp bubble shows a profound evolution in thought. Each era's understanding was a stepping stone, building toward today's radical questions. We are now asking if we can create or control gravity itself for thrust. It prompts a deeper reflection. Are we standing at the edge of a shift as monumental as the move from steam power to electricity? This historical context is not just a lesson. It is the essential foundation for understanding the bizarre and brilliant drives that are actively challenging these age-old principles right now. A sealed metal chamber shaped like a blunt cone and buzzing with invisible microwaves became the center of a firestorm in modern physics. This was the EmDrive, a device that promised to push against nothing and somehow move forward. Invented by Roger Scheuer, its principle was deceptively simple. Microwaves bouncing around inside its asymmetrical cavity were supposed to create a net force, a push toward the wider end. It was an engine with no flame, no exhaust, and according to most physicists, no possible way to work. It seemed to blatantly ignore Newton's third law. You cannot push against the inside of your car to make it move forward, and a sealed box should not be able to propel itself. Yet, when NASA Advanced Eagleworks Lab tested it, their delicate instruments registered a whisper of thrust. The signal was tiny, barely distinguishable from the noise, but it was enough to ignite a fierce debate. Was this a glimpse of new physics, or just an experimental mirage? Skeptics proposed alternative explanations, like magnetic interactions with the Earth's field or subtle thermal effects that could mimic thrust. A team in Germany, for example, also measured a force but concluded it was likely caused by the laboratory environment itself, not by some revolutionary new principle. This is where the story gets deeply theoretical. Some researchers suggested the drive might be pushing against the quantum vacuum, a seething sea of virtual particles that pop in and out of existence. In this view, space is not empty. It is a frothing medium that could, in theory, serve as a propellant. Most mainstream physicists find this idea unconvincing, pointing out that the quantum vacuum lacks the properties needed to be pushed against in this way. The EmDrive stands as a powerful cautionary tale. It represents the razor's edge between a world-changing discovery and a stubborn artifact of measurement error. It forces us to ask a profound question. Are we seeing a failure of the experiment or a first crack in the foundation of our most trusted laws? This controversy, however, did not end the search. It merely sharpened it, leading scientists to explore other theoretical pathways that might achieve the same goal without the same philosophical paradoxes. The EmDrive controversy forced physicists to look deeper, beyond simple mechanics and into the bizarre heart of quantum reality. What if the void of space is not empty at all? Quantum field theory paints a startling picture, describing the vacuum as a seething sea of virtual particles. These are not real particles in the traditional sense, but fleeting fluctuations in energy that pop into and out of existence in an endless, frothing dance. This quantum foam is not just a theoretical curiosity. It possesses real energy, often called zero-point energy, and it can even push. We have a direct demonstration of this in the Casimir effect. When you place two incredibly smooth, uncharged metal plates extremely close together in a vacuum, they are gently pulled toward each other. Why? Because the bustling crowd of virtual particles that can exist outside the plates exerts more pressure than the limited range of fluctuations that can fit between them. The void itself is pushing them together. This is a measurable force generated by the restless energy of empty space. The tantalizing proposal, then, is to build an engine that does not push against its own fuel, but against this quantum sea. A quantum vacuum thruster would aim to create an asymmetry, a kind of quantum pressure differential, to produce a net push in one direction. Think of it not as a rocket, but as a subatomic sail. Instead of catching photons from the sun, this sail would catch the relentless push of virtual particles. Physicists like Harold White have speculated that by manipulating quantum fields with precision, perhaps using advanced metamaterials, we could focus this vacuum energy and generate directional thrust. The concept is rooted in the established mathematics of quantum electrodynamics, which accurately predicts these strange effects. But the path from theory to a working engine is astronomically difficult. The energy densities involved are almost incomprehensibly vast, and our ability to control them is, for now, non-existent. We are trying to build a ship to sail on a sea that flashes in and out of reality 1 trillion times a second. The risk is that we are chasing a theoretical ghost, a phenomenon that cannot be meaningfully harnessed. Yet, the possibility remains profoundly alluring. If we could ever learn to engineer the quantum vacuum, we would no longer be travelers in space. We would become sailors on the fundamental fabric of reality itself. This quest pushes our understanding of gravity to its absolute limit, forcing us to ask if we can not just ride these quantum waves, but actually bend the geometry of the universe to our will. A spacecraft sits perfectly still, yet the universe rushes past it. This is the promise of the Alcubierre warp drive, a vessel that does not move through space, but instead moves space itself. Envision a bubble of distorted reality surrounding the ship. According to Einstein's equations, the fabric of spacetime in front of the bubble is violently compressed, while the space behind it expands at an incredible rate. The ship inside this warp bubble is carried along on this wave, like a surfer on a cosmic tide. It never accelerates, so the crew feels no crushing G-forces, and it never breaks the speed of light within its local frame. Yet, the space around it moves so dramatically that the ship could cross interstellar distances faster than a beam of light traveling through normal space. This is not magic. It is a direct, albeit extreme, solution to the equations of general relativity, first proposed by Miguel Alcubierre in 1994. The catch, and it is a monumental one, is the fuel. To warp spacetime in this way requires something with negative energy density, a substance that gravitationally repels rather than attracts. We do not find this in the normal matter of our world. We must look to the theoretical realm of exotic matter or peculiar states of quantum fields, like the Casimir effect, which can exhibit these negative pressure characteristics. For decades, the energy requirement was calculated to be absurdly vast, on the scale of converting entire Jupiter-sized planets into pure energy. But then physicists like Sonny White proposed a breakthrough. By changing the geometry of the warp bubble from a flat ring to a more dynamic, oscillating shape, the energy needed could be reduced from astronomical to something potentially within the realm of future engineering, perhaps equivalent to the mass of a small spacecraft. This brings the concept from pure fantasy into the arena of theoretical engineering. The question then becomes, how could we ever build such a thing? It would likely require stable wormholes to source the exotic matter, or metamaterials engineered at a quantum level to manipulate spacetime itself. Recent laboratory experiments have added a spark of intrigue. Certain laser configurations, when fired in precise ways, have produced simulations and minute measurements that some interpret as the first nascent signatures of a warp effect. These are not functional drives, but they hint that the physics might not be entirely out of reach. This entire endeavor forces a profound ethical reflection. If humanity gained the power to crumple and stretch the cosmos for its own travel, what responsibility would that entail? We would no longer be mere inhabitants of spacetime, but its architects. The line between a propulsion system and a universe-shaping tool begins to blur, pushing us to consider not just if we can, but what it means to wield such control over the fundamental geometry of existence. A tiny crystal buzzing with electricity could hold the key to inertia itself. This is the Mach Effect thruster, a device that proposes a truly radical idea. What if an object's mass is not a fixed, intrinsic property, but something that can be made to fluctuate? This concept reaches back to the philosopher Ernst Mach, who suggested that an object's inertia, its resistance to acceleration, is not generated locally. Instead, it arises from its gravitational interaction with all the distant mass in the universe. Every star and every galaxy contributes a tiny pull that gives matter its substance. James Woodward took this idea and pushed it into the realm of engineering. His proposed thruster uses piezoelectric crystals, materials that change shape when you apply an electric voltage. By driving these crystals with a rapidly oscillating current, he forces them to expand and contract millions of times per second. According to his models, when you accelerate a mass while its mass is momentarily increased by these Machian effects, and then decelerate it when its mass is decreased, you can produce a net thrust. The engine pushes against the cosmic background of the universe itself without throwing anything overboard. It is an attempt to turn the entire cosmos into your reaction mass. In laboratory vacuum tests, researchers have reported small but persistent thrust signals that align with these predictions. The measured forces are minuscule, often on the scale of micronewtons, but they appear even after teams meticulously account for experimental errors like magnetic interactions or thermal expansion. One anecdote from Woodward's lab describes the thrill of seeing that signal hold steady, a faint but stubborn push that refused to vanish under scrutiny. This persistent data fuels deep optimism among a small community of propulsion physicists. Yet, the scientific mainstream remains deeply divided. The device presents immense engineering challenges, particularly in vibration damping. How do you distinguish a genuine thrust from the overwhelming mechanical noise of something vibrating at such high frequencies? Peer-reviewed analyses fiercely debate whether the observed effect is a real breakthrough in physics or a sophisticated artifact of the complex experimental setup. The electrical input requirements are also substantial, and the thrust-to-power ratio remains very low. But the underlying question is what truly captivates the imagination. If inertia is not an absolute wall but a dynamic relationship with the universe, then perhaps we can learn to tune it. Can we find a way to reduce an object's inertial mass, making it effortlessly easy to accelerate? Or could we even cancel it out entirely, effectively engineering gravity itself? The Mach Effect thruster is more than just another experimental device. It is a tangible, if contentious, probe into the deepest nature of matter and motion. It suggests that the power for our journey to the stars may not be locked in a fuel tank, but woven into the invisible connections that bind us to the cosmos. Riding the ripples of spacetime itself is the ultimate form of surfing. Gravitational waves are not mere echoes of cosmic violence. They are the literal stretching and compressing of the universe's fabric, a phenomenon predicted by Einstein and spectacularly confirmed by observatories like LIGO. These waves carry energy and momentum across the cosmos. The radical proposition is to stop just listening to them and start riding them, using a gravitational wave drive to sail on these cosmic undulations. Think of a surfer waiting for the perfect wave. Now, replace the ocean with space-time and the surfboard with a starship. As a gravitational wave passes, it would rhythmically distort space around the vessel. A ship tuned to this frequency could, in theory, extract momentum from the wave, pushing itself forward by essentially pushing back against the ripple in reality. Experts like Dr. Lance Dixon have pondered whether highly advanced civilizations might already use such phenomena for travel, turning the background hum of the universe into an interstellar highway. The fundamental challenge is one of scale. The gravitational waves we detect from events like merging black holes are unimaginably powerful, but their effect on matter is infinitesimally small, far weaker than the gentlest breeze. To use them for propulsion, we would need to generate our own powerful, high-frequency waves, a feat far beyond our current capabilities. The energy required to produce even a faint, detectable artificial gravitational wave is staggering, likely demanding the total conversion of a planet's mass into pure energy. So how could it ever work? One hypothetical design involves colossal superconducting rings, cooled to near absolute zero and spun at relativistic speeds. By creating a rapidly oscillating mass distribution, this engineered resonator could, in theory, emit a controlled directional ripple in spacetime. This is not a gentle push but a fundamental shaking of the universe's foundations, a controlled tremor aimed at pushing a ship forward. The dynamics are utterly different from electromagnetic waves. Light can be reflected or absorbed by a sail, but a gravitational wave interacts with the very mass energy of an object, shaking space itself. This means a gravitational wave sail would not be a shiny sheet of mylar, but the entire structure of the spacecraft, engineered to resonate in harmony with the artificial spacetime ripples it creates. Are these waves the ultimate highway for interstellar voyages? the cosmos seems to use them as its primary method of communication for the most energetic events. Tapping into that power would be the final step in our transition from being passengers on spacetime to becoming its pilots. This staggering ambition forces the next logical question. What kind of materials could possibly withstand such forces or even generate them? The answer may lie not in the metals of today, but in the metamaterials of tomorrow. A disk of supercooled ceramic hangs silently in the air, but its true mystery lies not in its levitation, but in what it might be doing to gravity itself. This was the stunning claim from Russian physicist Eugene Podkletnov in the 1990s. He reported that a rapidly spinning superconductor, specifically a compound of yttrium barium copper oxide cooled to extreme temperatures, could create a shield. Objects placed above this spinning disk seemed to lose a small percentage of their weight, as if gravity's relentless pull was being subtly muted. The implications were staggering. A genuine gravity shield would shatter our understanding of propulsion. Instead of fighting Earth's gravity with a column of fire, a spacecraft could simply turn on a device to make itself lighter, or perhaps even weightless, requiring only a whisper of thrust to ascend into orbit. The theoretical basis for this reaches into the deepest questions of physics, suggesting a link between superconductivity and gravity. In a superconductor, electrons pair up and move without resistance, forming a macroscopic quantum state. Some theories, like those tying general relativity to quantum mechanics, propose that this coherent state of matter could somehow interact with the gravitational field, perhaps by altering the local curvature of spacetime around the device. The high-speed rotation is thought to be crucial, possibly amplifying this effect or creating a structured field. The quest to verify this has been a scientific roller coaster. NASA and other institutions have attempted precise replications of the Podkletnov experiment. In some setups, sensitive instruments did register tiny, anomalous weight reductions. But the effect is elusive, often vanishing when researchers change conditions or tighten their controls. The central challenge is isolating a gravitational signal from a storm of other forces. A spinning superconductor is a powerful electromagnetic environment, and effects like air currents, subtle magnetic interactions, or even seismic vibrations can easily mimic the faint signature of a gravity shield. Most mainstream physicists view the Podkletnov effect as an unproven anomaly, likely a measurement artifact rather than a new force of nature. Yet, the idea persists because the potential reward is so immense. It forces a profound question. What if we are not just passengers subjected to gravity, but future architects who could one day design it? This pursuit pushes material science to its absolute limits, guiding us toward the exotic theories that might finally explain how matter, energy, and spacetime are woven together. The universe is not just expanding, it is accelerating, flying apart at a rate that defies the pull of all its gravity. This cosmic acceleration is driven by the most dominant force in our cosmos, a mysterious presence we call dark energy. It permeates every cubic centimeter of empty space, a latent power pushing the galaxies apart. What if we could tap into this ocean of cosmic repulsion? Theoretically, if a spacecraft could somehow couple itself to this expanding fabric, it would not need to push against anything. It would simply ride the tide of the universe itself, an expansion drive surfing on the stretching of spacetime. Cosmologists like Sean Carroll describe dark energy as having a negative pressure. This is not like air pressure, but a property of the vacuum of space that causes it to push outward to anti-gravitate. In our leading model of the universe, the Lambda CDM model, dark energy makes up about 70% of all the energy density in the cosmos. It is the background against which all other cosmic dramas play out. The thought experiment is breathtaking. Imagine a vessel that generates a localized field matching the properties of dark energy. Around the ship, spacetime would begin to expand, creating a repulsive gravity effect that pushes it away from everything else. You would not be burning fuel. You would be commanding a tiny piece of the cosmos to inflate, using the same mechanism that drives the fate of the entire universe. The engineering challenges are, of course, beyond colossal. We do not know what dark energy is. We only see its gravitational effect on the largest scales. We have no idea how to contain it, focus it, or even interact with it directly. It may be an untappable background, a fundamental stage on which we are merely players. Yet the possibility forces a profound shift in perspective. Our search for propulsion has escalated from manipulating objects within space to bending space itself, and now to potentially harnessing the very engine of cosmic evolution. Is dark energy the final, unbreachable frontier for our technology, or is its mystery simply a placeholder for a force we have not yet learned to engineer? To even ask this question is to expand our view of physics, pushing us to consider how the entire framework of our reality must evolve to make such a journey possible. Inside a pristine vacuum chamber, a device no larger than a coffee mug hums with electrical current. This is the cutting edge of propellantless propulsion research, where teams across the globe are building and testing real hardware. Laboratories at institutions like the University of Dresden and private ventures such as IVO Limited are creating prototypes of Mach Effect thrusters and quantum vacuum plasma actuators. Their goal is audacious: to generate a whisper of thrust, mere micronewtons of force, using nothing but electricity. For scale, a micronewton is about the weight of a single human eyelash. Yet, if real and scalable, that tiny push could be enough to maintain a satellite's position for decades, or slowly accelerate a probe on an interstellar trajectory. The core challenge is isolating this minuscule signal from a universe of noise. Researchers use exquisitely sensitive torsion balances, where the thruster is suspended on a fine wire. Any force it produces causes a tiny, measurable twist. The entire apparatus is sealed inside a high vacuum chamber to eliminate the faintest push from residual air molecules. Every wire must be meticulously routed, every magnetic field mapped and cancelled out, and the device's own thermal expansion calculated down to the nanometer. Veteran engineers like Richard Manser stress that this painstaking process is the only path to credibility. The difference between a new force of nature and a subtle experimental error can be thinner than an atom. One team recently celebrated a promising data run, a clean thrust signal that persisted for days, but when they reconfigured the setup for a confirming test, the signal vanished completely. This volatility is the field's defining frustration. It points to hidden variables, perhaps a specific resonance frequency or an unknown material property that unlocks the effect only under perfect, unrepeatable conditions. This leads to a difficult balancing act. How do we encourage the radical innovation needed to shatter paradigms while demanding the rigorous skepticism that separates truth from wishful thinking? The answer lies in the slow, meticulous work happening in these labs right now. Each failed replication and each transient signal is a data point, guiding us closer to understanding whether these measured forces are the first tremors of a physics revolution or just the echoes of our own instruments. A physics textbook's most sacred pages are now being questioned. They enshrine the conservation of energy and momentum as unbreakable rules, the bedrock upon which all of classical and modern physics is built. Yet massless drives present a direct challenge, promising thrust from a sealed box with no exhaust. If a closed system accelerates, where is the equal and opposite reaction? Where does the momentum go? This is the fundamental paradox that physicists like John Baez emphasize. He and many others argue that true propellantless propulsion is a misnomer. Momentum must always be exchanged with something. That something might not be a tank of chemical fuel. It could be the gravitational field of the Earth, the quantum vacuum, or the very curvature of spacetime. But it is not nothing. The drive is not massless in the sense of being reactionless. It is pushing against a hidden partner in the cosmic dance. To understand why this is so non-negotiable, we must look to a profound piece of mathematics known as Noether's theorem. Formulated by Emmy Noether over a century ago, it reveals a breathtaking connection between symmetry and conservation. The theorem states that for every continuous symmetry in nature, there is a corresponding conservation law. The fact that the laws of physics are the same today as they were yesterday, a symmetry in time, leads directly to the conservation of energy. The fact that the laws of physics are the same here as they are in a distant galaxy, a symmetry in space, leads to the conservation of momentum. These are not just rules we made up, they are fundamental properties of our universe's geometry. So how could any drive possibly circumvent this? The proposed solutions are as bizarre as the drives themselves. They suggest these devices might satisfy the global conservation laws by interacting with hidden degrees of freedom. A warp drive, for instance, uses a region of negative energy, while the spacecraft inside the bubble gains positive energy and momentum. The distorted spacetime around it carries an equal and opposite amount of negative energy and momentum. From a universal perspective, the total sum remains zero. Everything is conserved, but the local reality for the astronaut appears to break the rules. The quantum vacuum thruster proposes a similar balancing act, where the momentum of the spacecraft is offset by an equal and opposite momentum imparted to the quantum fields. We are not breaking the laws, we are just finding new, far more complex ledgers in which to keep the accounts. This forces a monumental question upon us. Are the persistent thrust signals from these experiments the first hints of a new chapter in physics, one where we finally learn to read those hidden ledgers? Or are they the ultimate demonstration of the law's unyielding power, showing us that every apparent violation is merely our own ignorance of where the reaction is truly occurring? Confronting these theoretical obstacles head-on is what separates science fiction from scientific frontier. It prepares us for the final, crucial step, moving from the blackboard to the laboratory, to see if any of these ideas can survive direct, unambiguous experimental scrutiny. A global network of laboratories now functions as a crucible for these radical ideas. Teams in Germany, China, and the United States set up identical experiments, following the same blueprints to build their own versions of the EmDrive or Mach Effect thrusters. Yet their results are a chorus of contradiction. One lab detects a persistent, if tiny, thrust signal. Another, using equipment of comparable sensitivity, finds nothing but null results and noise. This is the replication crisis at the bleeding edge of physics, a modern echo of the cold fusion saga that divided the scientific community decades ago. The core problem is the signal itself. The thrust these experiments hope to find is minuscule, often measured in micronewtons. Isolating such a faint push is like trying to hear a single violin note in a hurricane. Researchers must account for a myriad of mundane forces that can perfectly mimic the effect they seek. Take thermal expansion. As the electrical components in a thruster heat up, the metal itself expands by microscopic amounts. This thermal creep can exert a force on the sensitive torsion balance that is indistinguishable from the thrust of a new physics. Then there are Lorentz forces, subtle interactions between the electrical currents in the device and the Earth's own magnetic field. A landmark 2018 study on an EmDrive prototype concluded that the thrust signal they observed completely vanished once they properly modeled and accounted for these magnetic pushes. It was not a warp drive, it was a sophisticated compass needle aligning with the planet. Experts like Dr. Jose Rodel argue that the path forward requires a new level of experimental rigor. This means pre-registering studies, where scientists publicly declare their methods and analysis plans before they even collect data, preventing any subconscious bias from shaping the results. It demands better instrumentation, perhaps devices suspended not just in a vacuum, but in a chamber that actively cancels out the Earth's magnetic field. The calibration process itself becomes a high-stakes art. Engineers use precise electrostatic forces or known photon pressures from lasers to carefully calibrate their thrust scales, ensuring they know exactly what 1 micronewton of force looks like on their apparatus. Only then can they have confidence in any anomalous signal that appears. This leads to a profound and unsettling question. How do we navigate a landscape where proof is so elusive, where every promising result is shadowed by a plausible conventional explanation? The standards we set for this fringe science are a tightrope walk. We must be open enough to not stifle a potential revolution, yet skeptical enough to not be fooled by our own desires. The entire experimental pursuit is a testament to human patience, a slow, meticulous sifting of data in the hope of finding one glittering truth amid a mountain of doubt. This arduous search for a verifiable signal forces us to look up from the lab bench and ask a bigger question. What would it actually take to build a real machine, and what would happen if we succeeded? The faintest push could rewrite our entire future in space. Picture a fleet of small satellites, each no bigger than a shoebox, scattered throughout Earth's orbit. Today, their lives are cut short by the finite fuel they carry for station keeping, the delicate adjustments needed to hold their position. With even a whisper of continuous thrust from a massless drive, these CubeSats could maintain their orbits for decades, not years. Their instruments could monitor our planet's climate or form vast communication networks, all while maneuvering with an agility that is currently impossible. This is not just about longevity, it is about capability. Agencies like the European Space Agency are actively investigating how these microthrusters could enable radical new mission profiles. A satellite could continuously dodge space debris, performing elegant collision avoidance maneuvers without ever worrying about running out of propellant. It could use its nearly limitless thrust to finely tune its orbit, harvesting constant solar power to feed its enigmatic engine. The implications ripple outward from Earth. Consider a mission to Mars. A conventional spacecraft follows a ballistic arc, a fuel-efficient but slow trajectory dictated by orbital mechanics, but a vessel with a constant, low-thrust drive would not coast. It would accelerate continuously, pushing gently but relentlessly for the entire journey, cutting transit times in half without the colossal mass penalty of chemical propellant. The ship becomes a true vessel of the void, not a thrown rock. This principle finds its ultimate expression in projects like Breakthrough Starshot, which plans to use light sails propelled by powerful lasers. While the sail itself has mass, the photons pushing it do not, making it a close cousin to these other massless concepts. A swarm of tiny probes could be accelerated to a fraction of light speed, reaching our nearest stellar neighbor within a human lifetime. The economic transformation would be just as profound. By slashing launch mass and eliminating refueling missions, access to space would become dramatically cheaper. This opens the final frontier not just to superpowers, but to universities, small companies, and emerging nations. The very infrastructure of our civilization could extend into the solar system, built on the back of engines that push against the universe itself. What kind of new industry and discovery would that unprecedented access unleash? The roar of a rocket launch could become a relic of a more primitive age. Envision a future launch pad not shaking with violent combustion, but humming with the quiet power of a massless drive lifting a sleek vehicle into the sky. The most immediate transformation would be economic. The staggering cost of reaching orbit, currently measured in thousands of dollars per pound, would plummet. The fuel itself is often the single greatest mass and expense in a traditional rocket. Remove that burden, and access to space shifts from a monumental national endeavor to a routine commercial flight. Economic analyses like those from space economist Dr. Alex MacDonald suggest this could trigger a golden age of space development. The savings would cascade through every aspect of the industry. New sectors would emerge almost overnight. Factories operating in the perfect vacuum of orbit could manufacture pharmaceuticals and advanced alloys impossible to create on Earth. The dream of asteroid mining, once a fantasy, becomes a plausible venture when you can send small, efficient tugs to nudge resource-rich asteroids into stable orbits using only electricity. Orbital habitats for research and tourism transition from science fiction to feasible construction projects, funded by the colossal savings on construction material delivery. This economic earthquake would create a surge of new jobs, but not in the factories that build giant rocket stages. The demand would shift to a new workforce of physicists, metamaterial engineers, and quantum systems technicians, all specializing in the intricate science of these new drives. Entire companies dedicated to maintaining and operating these propulsion systems would form a new industrial backbone. Conversely, the traditional rocket manufacturing sector would face a slow but inevitable obsolescence, much like the companies that once built steam locomotives. This rapid expansion necessitates entirely new rules of the road. How do we manage orbital traffic when thousands of small, highly maneuverable satellites can flit about with near impunity? Global regulatory frameworks would need to be established to prevent collisions and manage space debris, turning what is now a sparse highway into a bustling, organized metropolis. Consider the impact on global connectivity. Today's satellite internet constellations are limited by the lifespans and orbital slots of their components. With propellantless thrusters, these satellites could actively maintain their positions for centuries and dynamically reposition themselves to provide optimal coverage. This would allow for a rapid, low-cost expansion of these networks, potentially bridging the digital divide for remote and underserved communities across the globe. Such a powerful technological shift forces a critical ethical question. How do we ensure this new access to space benefits all of humanity, rather than becoming the exclusive domain of a few wealthy corporations or nations? The economic prospects are dazzling, but they underscore an urgent need to confront the societal and ethical dimensions that such control over physics would inevitably unleash. Such power demands a deeper responsibility. The moment we unchain ourselves from the rocket's fiery plume, we face a new set of societal and ethical questions that are as vast as space itself. Who gets to wield this technology? The risk of a technological monopoly is stark. If only a handful of corporations or nations can initially develop and control massless drives, it could create a permanent and unbridgeable gap, a new kind of inequality that extends from Earth's surface to the asteroid belt. We could see a future where the wealthy become the spacefaring, while the rest of humanity remains gravity-bound, watching from below. Ethicists like Dr. Keith Ebnai warn that this demands proactive governance. He suggests we need international treaties for advanced propulsion, similar in spirit to nuclear non-proliferation agreements. The goal would be to prevent an arms race in space, to ensure these drives are used for peaceful exploration and economic development, not for dominating celestial territories or weaponizing orbits. This is not just about preventing war, it is about stewardship. Consider a pristine ice field on Europa. A conventional mission might land a single probe with minimal contamination. But a fleet of cheap, agile ships powered by massless drives could swarm the moon, potentially disrupting an alien biosphere we have not even discovered yet. Our very ability to travel easily could become our greatest liability, forcing us to adopt a prime directive of our own making long before we encounter another intelligence. The cultural shift would be profound. As access to space becomes routine, our identity as a planetary species would begin to fade, replaced by a new consciousness as a spacefaring civilization. This expansion could unify humanity under a common goal, or it could magnify our existing divisions, projecting old conflicts onto a new, solar system-wide stage. The moral imperative is clear. We must explore, but we must do so with a commitment to responsibility woven into the very fabric of our journey. This profound responsibility, however, is balanced by a tremendous potential benefit, one that brings our story full circle, back to the environment of our own fragile planet. A silent ascent leaves no toxic trace in the sky. This is one of the most immediate and profound environmental gifts of massless propulsion. Today, every rocket launch is a spectacular but dirty event, injecting tons of black carbon and other particulates directly into the pristine upper atmosphere. These particles act like a thin, dark blanket, absorbing solar radiation and contributing to atmospheric warming in a layer that is exceptionally sensitive. A shift to drives powered by electricity, especially if that electricity comes from renewable sources, would eliminate this form of pollution entirely. The sky would no longer bear the chemical scars of our ambition. The sustainability extends far beyond the launch itself. Consider the entire life cycle of a traditional rocket, from the mining of its fuel components to the fiery disposal of its massive stages. Each launch is a linear, consumptive process that leaves a trail of debris in its wake. Massless drives, by contrast, represent a circular model. Their primary input is energy, which can be generated and regenerated indefinitely from solar panels in space. Their components, while complex, are built to last for decades of continuous operation, drastically reducing the stream of new hardware that must be manufactured and launched. Dr. Moriba Jah, a leading expert on space sustainability, forcefully argues that our future in space depends on this kind of innovation. He points out that our current practices are creating a shell of orbital debris that threatens every satellite and mission. A key benefit of propellantless systems is their role in mitigating this crisis. Without the need to jettison empty fuel tanks and spent upper stages, we stop adding the largest and most dangerous pieces to the orbital junkyard. Satellites equipped with these drives could also actively deorbit themselves at the end of their lives, gently guiding themselves to a controlled re-entry instead of becoming decades-long collision hazards. This aligns perfectly with United Nations guidelines for the long-term sustainability of outer space activities. The most hopeful vision lies in the synergy with renewable energy. A spacecraft with a massless drive is essentially a mobile platform that can be perpetually powered by the sun. This creates a closed, clean loop. The energy to leave Earth, to travel to Mars, and to explore the asteroids would come directly from the cosmos itself, not from burning limited planetary resources. We must confront a pivotal question as we stand on this threshold. Can our greatest technological leap also be the one that finally allows us to explore the cosmos without harming our celestial home? The answer depends entirely on the materials we create to harness these subtle forces. turning a theoretical promise into a tangible, sustainable future. The airless void of space hides a subtle, brutal environment that would tear conventional metals apart. We can dream of warp bubbles and quantum sails, but without the right materials to build them, these concepts remain elegant equations on a chalkboard. The true engine of our propulsion revolution may not be a blueprint, but a new periodic table filled with substances that defy our everyday experience. Physicist Dr. Anna Zaniewski describes this as the ultimate engineering race, a global effort to create metamaterials, substances engineered to have properties not found in nature. The most sought-after prize is a material with effective negative mass, something that would gravitationally repel ordinary matter. While we have not created a true negative mass, certain metamaterial structures can mimic this behavior for specific energy fields, a crucial first step for stabilizing a warp-drive spacetime geometry. These are not just stronger alloys, they are architected matter, designed atom by atom to interact with the universe in ways nature never intended. Strength alone is not enough. The materials must also channel immense energy densities without vaporizing. This is where nanotechnology enters the stage. Carbon nanotubes and graphene composites offer a potential solution. These are not just strong, they possess extraordinary thermal conductivity, meaning they can siphon away the devastating heat generated by a quantum vacuum plasma or a warp field resonator. Picture a network of carbon nanotubes woven into a shield, acting like a cosmic heat sink, radiating energy away from the core of the drive. The structure of these materials is everything. A warp field resonator would not be a solid block of metal. It would be a delicate gossamer lattice, a three-dimensional tapestry designed to vibrate in harmony with spacetime itself. Any imperfection, any microscopic crack would disrupt this delicate resonance and collapse the entire effect. The manufacturing challenge is staggering. We are moving beyond forging and milling into the realm of atomic-scale printing, where we assemble these materials layer by layer, almost like growing a crystal to a precise, complex blueprint. Durability introduces another brutal test, the relentless rain of space radiation. Cosmic rays and solar flares can degrade conventional electronics and materials over time. A vessel relying on the flawless quantum coherence of a superconductor cannot afford this slow decay. The material must be self-healing, or at least radiation-resistant, maintaining its exotic properties for decades amidst a hail of high-energy particles. Recent breakthroughs in high-temperature superconductors offer a glimmer of hope. For decades, superconductivity required cooling materials to temperatures near absolute zero, an impractical burden for a spacecraft. New ceramic compounds now achieve this zero-resistant state at much higher, more manageable temperatures. This single advance makes experiments like the Podkletnov gravity shield vastly more practical to test and eventually to deploy. The dream of room-temperature superconductivity drives entire research departments, for the material that achieves it would not just revolutionize power grids on Earth. It would become the bedrock of our interstellar ambitions. Yet a material discovered in a lab is useless if it cannot be manufactured at scale. How do you produce kilometer-long sheets of flawless graphene or perfect crystals of a novel metamaterial? The path from a 1-gram sample in a vacuum chamber to an industrial production process is a frontier in itself. It demands a new kind of factory, one that operates with the precision of a semiconductor fab, but on a scale suited for building spacecraft hulls and drive cores. This immense investment in material science is not a separate endeavor from propulsion. It is the very foundation. Every theoretical drive we have explored is shackled, waiting for a substance strong enough, clever enough, and resilient enough to bring it to life. The creation of these materials will be a quiet, unglamorous revolution, happening in clean rooms and under microscopes, but it will ultimately determine whether our ships remain forever grounded or finally learn to dance on the fabric of spacetime. And to make them dance, we must ask where the power for this cosmic ballet will come from. A warp drive does not just bend space, it demands an astronomical price in energy. Early calculations for the Alcubierre design were sobering, suggesting you would need to convert a planet like Jupiter entirely into pure energy just to create a single microscopic warp bubble. This was a number so vast it seemed to slam the door on the concept forever, but physics is a living conversation. Later refinements by researchers like Dr. Harold White suggested that by oscillating the warp bubble's geometry, shifting its shape from a flat ring to a more dynamic toroid, the energy requirement could plummet from a planetary scale down to something almost conceivable, perhaps the mass energy of a small spacecraft. That is still a staggering amount of power, translating to a need for gigawatts of continuous output, enough to power a major city, all focused into a propulsion system. This is the fundamental bottleneck. The most elegant drive concept is useless without a power source that is both unimaginably potent and, for a spacecraft, feasibly light. The traditional answer has been nuclear fission, but its energy density is simply too low for this new class of engine. The next step is nuclear fusion, which taps into the power of the stars themselves. A working fusion reactor could provide the dense, sustained power needed for a high-thrust Mach Effect device or a sustained quantum vacuum plasma. Yet even fusion has its limits. To reach for the warp drive, we must look to the ultimate energy source, matter-antimatter annihilation. This process converts 100% of mass into energy, making it the most energy-dense reaction known to physics. A single gram of antimatter reacting with a gram of matter releases a cataclysmic burst of energy, rivaling a small nuclear bomb. Taming that power for a controlled, steady thrust is a challenge that lies far beyond our current engineering. How do you store antimatter without it touching any ordinary matter and annihilating? Magnetic bottles are the theoretical solution, but constructing one that is perfectly reliable for years of space travel is a monumental task. For drives that operate closer to home, beamed power offers a clever alternative. Imagine a constellation of giant solar satellites in high Earth orbit, collecting endless sunlight and converting it into a tightly focused microwave or laser beam. This energy could be projected onto a distant spacecraft, powering its drive without the craft needing to carry its own reactor. This is the principle behind light sails, the only truly massless propulsion method we have successfully demonstrated. A spacecraft catches the momentum of photons, whether from the sun or a powerful laser, and is pushed forward. But for an EmDrive or a Mach thruster, which needs internal electrical power, beamed energy would have to be converted back into electricity on the craft, adding complexity and weight. This leads to the critical question of energy storage and efficiency. Even with a fantastic power source, you need a way to deliver that energy in a controlled burst. Superconducting batteries, which can store immense electrical charge with almost no loss, become essential. They would act as a buffer, smoothing out power delivery to the drive. Yet every conversion of energy introduces losses. Heat is the eternal enemy. If your drive is only 1% efficient at converting electrical input into thrust, 99% of your precious power is wasted as heat, which must then be radiated away into the cold vacuum, requiring massive and heavy cooling systems. This efficiency problem is the silent killer of many propulsion concepts. The raw physics of a warp bubble might one day be possible, but if it requires 10 gigawatts of power and is only 0.01% efficient, the practical machine would be a slow, glowing oven drifting through space. This forces us to confront a humbling reality. Our grandest propulsion dreams are not just waiting for a blueprint. They are waiting for a power revolution, one that may very well redefine our relationship with energy itself, not just in space but here on Earth. A single equation can hold the blueprint for a new reality. These massless drives are not just engineering challenges. They are profound puzzles for theoretical physics, demanding we re-examine the very rules of the cosmos. On blackboards around the world, physicists are wrestling with the deepest frameworks we have, from Einstein's general relativity to the bizarre probabilities of quantum mechanics. They are asking if these theories need to be subtly modified or perhaps radically extended to explain how a closed system can ever gain momentum. The quest often leads into the most abstract territories of modern science. String theory, for instance, proposes that our universe has more than the three spatial dimensions we experience. Could the momentum from a massless drive be secretly transferred into these hidden, curled-up dimensions, preserving the overall balance of the universe in a way we cannot directly see? Similarly, loop quantum gravity, which describes space as a network of tiny, discrete loops, might allow for a novel kind of momentum exchange with the fabric of spacetime itself. These are not just ideas, they are potential pathways to a working engine, but they remain trapped in the realm of mathematical elegance, awaiting any shred of experimental proof. Theoretical physicist Dr. Sabine Hossenfelder offers a crucial note of caution here. She argues that without empirical data to guide us, modifying our most successful theories risks creating an infinite playground of mathematical curiosities, each one perfectly self-consistent yet utterly detached from physical reality. The history of science is littered with beautiful ideas that simply were not true. To avoid this, physicists are exploring very specific extensions. Some models introduce torsion fields, which add a new twist to Einstein's gravity, suggesting that the spinning of particles could generate novel gravitational effects. Others look at scalar tensor theories where the strength of gravity is not a constant, but a dynamic field that could potentially be manipulated. The central, haunting question is this: do we need a final theory of everything, a single set of equations that perfectly unites gravity with the quantum world, before we can achieve gravity without fuel? Or is the answer hidden in a clever application of the physics we already possess, waiting for a lone experimenter to make a serendipitous discovery? This tension between mathematical beauty and experimental proof defines the entire endeavor. It forces us to look up from the blackboard and back into the laboratory, where the ultimate verdict on these theories will be delivered not by elegance but by evidence. Roger Scheuer's announcement in 2001 landed like a quiet bomb. His company, SPR Limited, claimed a device that defied Newton with a simple cone and some microwaves. The story did not go viral immediately. It simmered, a strange rumor on the fringes of physics, until larger institutions took notice. NASA Eagleworks Laboratory built its own replica, and when their papers reported a tiny, anomalous thrust, the world truly took notice. Media headlines screamed about the impossible engine, and online forums lit up with speculation, building a powerful narrative of a lone inventor challenging the scientific establishment. This public enthusiasm created a feedback loop, fueling further interest and even attracting unconventional funding from sources eager to back a winner. The journey of the EmDrive became a modern parable, not of a discovery, but of the entire scientific process under a microscope. Independent researchers across the globe joined the chase, each team refining the test setup. The earliest experiments used simple pendulum balances in air. Later, more rigorous attempts moved into sophisticated vacuum chambers, in an attempt to isolate the effect from every conceivable external influence. Yet with each new test, the results became a chorus of contradiction. One lab would detect a whisper of thrust, while another, using seemingly identical methods, found nothing but null results and noise. Expert critics like Dr. John Costella meticulously dissected the positive findings. He highlighted fundamental methodological flaws, pointing out that the thermal expansion of the device as it heated up could easily produce a force that mimicked thrust on a sensitive balance. Inadequate shielding from the Earth's magnetic field was another critical oversight, as the electrical currents in the drive could create a subtle push via Lorentz forces, perfectly impersonating the desired effect. The story took another dramatic turn with claims from a Chinese research team. They announced they had not only tested the EmDrive but had launched one into space on a satellite, suggesting it was operating successfully in orbit. This announcement created a fresh wave of excitement, but it was followed by a profound silence. The team provided no transparent data, no telemetry that could be independently analyzed, and no peer-reviewed papers. This lack of evidence ultimately fueled more skepticism than hope, serving as a cautionary tale about the difference between a press release and scientific proof. The entire EmDrive saga forces a difficult, reflective question. How do we, as a society, navigate the thrilling but treacherous landscape of fringe science? The lesson it offers is one of disciplined balance. We must remain open enough to radical ideas to not stifle a potential revolution, yet we must apply a level of rigor so severe that it can distinguish a new force of nature from the subtle creaks and groans of our own experimental setups. This case study illustrates the immense hurdles in moving from a captivating concept to validated reality, a path littered with both hope and hubris, pointing toward a future where our experiments must be even cleverer and our skepticism even sharper. A coordinated international effort is already taking shape to silence the debate. The path forward requires more than isolated labs. It demands a global campaign with standardized rules of evidence. Space agencies like NASA and the European Space Agency are drafting the blueprint for this new era of testing. Their goal is to create a universal protocol for evaluating propellantless thrusters, a checklist so rigorous that no conceivable source of error can hide. This means moving beyond simple torsion balances to instruments capable of sensing forces 1,000 times smaller. Imagine arrays of superconducting quantum interference devices, or SQUIDs, monitoring for minuscule magnetic fields, while laser interferometers measure thermal expansion down to the width of an atom. Artificial intelligence would then sift through this flood of data, learning to distinguish the unique fingerprint of a genuine thrust signal from the endless background murmur of noise. The roadmap for this quest is a patient, phased ascent. The first step unfolds on the ground, inside chambers where the vacuum is deeper than interplanetary space, and the temperature is cooled to within a few degrees of absolute zero. This cryogenic environment freezes out the thermal motion of atoms, quieting the molecular vibrations that can mask a tiny push. Only after a device consistently produces thrust in this pristine, silent laboratory will it earn a ticket to orbit. The next phase calls for in-space demonstrations, first on small CubeSats where a micronewton of force can produce a measurable change in velocity over weeks. A more ambitious test would attach a thruster to an external platform on the International Space Station, using the station's precise tracking systems to monitor for any acceleration in the microgravity environment. NASA's own technology classification system provides a framework for this gradual climb, categorizing these drives as low-technology readiness level concepts that must pass through a series of incremental gates. Each milestone, from basic proof of concept to a validated prototype, demands collaboration between academic theorists who refine the models and industrial engineers who can manufacture the exotic components. The ultimate validation would be a dedicated deep space probe. Picture a small spacecraft powered by solar panels and equipped with a Mach Effect thruster or a quantum vacuum plasma actuator sent on a trajectory away from Earth. Freed from atmospheric drag and planetary magnetic fields, its course could be tracked for years by global networks of radio telescopes. Any persistent deviation from its predicted ballistic path, any extra velocity gained without a plume of exhaust, would be the definitive signature of a new physics. Funding such a decades-long endeavor is its own monumental challenge, requiring a blend of public agency grants and visionary private investment. The timeline is not for the impatient. Current roadmaps suggest that if the ground-based results remain promising, we could see a conclusive in-space demonstration by 2040, with functional drives enabling new classes of solar system missions by the middle of the century. This entire experimental crusade rests on the people driving it forward. Who are the key players in this high-stakes pursuit, and what unites their diverse efforts? The global hunt for a new engine is a story of people, a diverse alliance of believers and skeptics pushing the boundaries of the possible. At NASA EagleWorks Laboratory, Dr. Harold White's team operates in a realm of high precision, their work focused on the subtle geometries of warp fields. They are not building a starship in a garage, but meticulously testing the mathematical theories of Alcubierre with laser interferometers, searching for any microscopic signature that spacetime can be engineered. Their funding comes through NASA's Innovative Advanced Concepts Program, a pipeline for ideas that sound like science fiction but are grounded in rigorous physics. A world away, in academic halls like the University of Dresden, researchers approach the puzzle from a different angle. Their labs are filled with the hum of vacuum chambers and the delicate apparatus of torsion balances, where they test Mach Effect thrusters built to the specifications of James Woodward. Woodward himself, a professor emeritus, represents the determined individual pioneer, working for decades with modest grants to refine a theory that much of the mainstream physics community initially dismissed. His published papers are a chronicle of persistent data, a record of tiny thrust signals that refuse to disappear. This ecosystem is vital, for it also includes the essential skeptics. Physicists like Dr. John Baez and Dr. Sabine Hossenfelder serve as the community's immune system, rigorously questioning results and demanding ever higher standards of proof. Their critiques, published in the same journals as the positive findings, force the entire field to be better, to eliminate every possible error. The collaboration extends beyond academia. Private companies like IVO Limited are now entering the fray, bringing an entrepreneurial speed and a focus on near-term applications. Their partnership with commercial satellite launchers aims to test a quantum plasma thruster in space, a venture that would be far slower if left solely to government timelines. This fusion of public research and private capital is accelerating the entire endeavor. The breakthrough initiatives funded by billionaires like Yuri Milner exemplify this new model, backing ambitious projects like Starshot that blend established physics with radical engineering. How does this complex network actually function? An illustrative case is the effort to test a thruster on the International Space Station. It requires a university team to design the experiment, an aerospace company to build the flight-ready hardware, and a space agency to provide the launch and a platform on the station. Each entity brings a unique piece of the puzzle, crossing the traditional boundaries between theoretical physics, mechanical engineering, and orbital operations. The presence of both visionary individuals and powerful institutions creates a dynamic tension. The lone theorist can propose a revolution, but it takes the resources of a national lab to subject it to the brutal test of reality. This collaborative spirit, this global brain trust, is what transforms a solitary equation on a chalkboard into a tangible device humming in a vacuum chamber. Their collective efforts, debated in journals and tested in orbit, are what the wider world ultimately sees, often filtered through a media lens that craves a simple, sensational story. A headline screams about an engine that breaks the laws of physics, only for a follow-up article to quietly declare it a dead end. This relentless cycle of hype and disappointment has defined the public story of massless drives, creating a roller coaster of belief that leaves many unsure what is real. Media coverage often seizes on the revolutionary promise of these technologies while glossing over the deep scientific uncertainties and the painstaking, often frustrating, work of replication. The story is framed as a binary, a simple battle between a visionary breakthrough and stubborn establishment denial, when the reality is a vast gray area of meticulous experimentation. Science communicator Dr. Neil deGrasse Tyson frequently emphasizes this crucial distinction, urging reporters to clarify the vast gulf between a tantalizing hypothesis and a proven, repeatable fact. He argues that the true story is not the single experiment that showed a positive result, but the dozen that followed it, seeking to tear it down. This balanced approach does not kill excitement. It builds a more resilient and authentic form of wonder, one grounded in the real, gritty process of discovery. The digital age has amplified this dynamic to an incredible degree. A single, slickly produced YouTube video showcasing a hovering device can garner millions of views and spawn countless hopeful articles, while the subsequent, dry academic paper reporting a null result from a peer-reviewed lab receives a fraction of the attention. Documentary features add to this, often using dramatic music and futuristic animations that imply these drives are just around the corner, rarely pausing to explain the decades of fundamental physics and material science that still stand in the way. The result is a public discourse filled with passionate enthusiasts who are convinced the technology is being suppressed, and equally passionate skeptics who dismiss the entire field as pseudoscience, with very few people discussing the actual, nuanced data. The EmDrive is the perfect case study. It became an online phenomenon, a symbol of rebellion against old physics, yet how many of its millions of followers could explain the replication crisis or the plausible alternative explanations involving thermal and magnetic effects? This gap between perception and reality is not harmless. It shapes everything. When public sentiment swings toward unbridled optimism, funding can flow into projects based more on promise than on solid evidence. When the inevitable disillusionment sets in, the entire field can be stigmatized, making it harder for legitimate, careful research to secure the resources it needs. The crucial question then becomes, how do we build a public conversation about cutting-edge science that is both inspiring and intellectually honest? The answer lies not in dimming the excitement, but in redirecting it toward the profound challenge of the scientific process itself, celebrating the slow, collective climb toward understanding. This public narrative, in turn, directly influences the investors and policymakers who hold the purse strings for our journey to the stars. A single promising signal can unlock a flood of capital. The financial landscape for these radical propulsion concepts is a high-stakes arena, a delicate dance between visionary government grants and daring venture capital. Agencies like DRRPA and the European Space Agency fund early-stage research through programs specifically designed for high-risk, high-reward ideas, where the goal is not a guaranteed product but a fundamental discovery. These initial grants are often modest, perhaps a few $100,000, just enough to build a prototype and conduct a preliminary test in a university laboratory. The recent successes of established electric propulsion systems, like the ion thrusters used on many satellites, have created a crucial foothold, demonstrating that alternatives to chemical rockets can offer real economic value. This track record makes investors slightly more willing to listen to the next, more radical pitch. Industry analyst Dr. Carissa Christensen points to a growing trend of private space companies, from small startups to giants like SpaceX, taking an interest. Their motivation is intensely practical. They see the potential for massive, long-term cost savings in satellite operations. A constellation of communication satellites that never runs out of station keeping propellant could generate billions in extra revenue over its lifetime, a powerful incentive to invest in the underlying physics. Alongside these traditional sources, a new model has emerged through crowdfunding platforms. When a company like IVO Limited raised money online to test its quantum plasma thruster in orbit, it was not just collecting dollars. It was building a community of believers, a base of public support that demonstrates a market for the technology beyond the cautious walls of government procurement. This diverse funding ecosystem is vital, but it faces a fundamental tension. How do you secure long-term investment for a technology that may not prove viable for 20 years and whose very principles are still debated in physics journals? Venture capital typically seeks returns within a 5 to 10-year window, a timeline that is often incompatible with the slow, meticulous pace of basic scientific discovery. This creates a funding valley of death, where promising ideas from academic labs struggle to find the sustained capital needed to mature into flight-ready hardware. The question then becomes urgent. What mixture of patient public funding, strategic corporate investment, and grassroots support can best nurture such a risky, transformative innovation? The answer will determine whether these engines remain fascinating experiments or become the foundation of our future in space. A micronewton of thrust is a whisper in a hurricane of engineering noise. Translating that fragile signal into a reliable engine demands a symphony of precision across every discipline. First is the environment, a vacuum deeper than anything found naturally in the solar system. Inside the test chamber, every stray air molecule must be eliminated, for their gentle push could easily mimic the very thrust we are trying to measure. This is not a simple empty space. It is an actively scrubbed void, achieved with cryogenic pumps that freeze out the last remaining atoms onto surfaces cooled to within a few degrees of absolute zero. Then comes the heat. These drives consume immense electrical power, and even with 99% efficiency, that remaining 1% of waste heat could vaporize the delicate components. Engineers like Dr. Paulo Lozano point to thermal management as the silent killer of advanced propulsion concepts. You cannot use fans or liquid coolants in space, so the entire system must radiate this energy away as infrared light, requiring vast, lightweight radiator panels that themselves add mass and complexity. The manufacturing tolerances are almost unimaginable. A Mach Effect thruster relies on piezoelectric crystals vibrating millions of times per second. Any microscopic flaw in the crystal lattice, any impurity smaller than a nanometer, disrupts the perfect harmonic resonance needed to generate the effect. The entire assembly must be machined with a precision finer than most microchips. Vibration control becomes a nightmare. How do you distinguish a genuine thrust from the overwhelming mechanical shudder of the device itself? The entire thruster must be suspended on active dampeners that sense these vibrations and cancel them out with counterpulses, a system so sensitive it can feel the footsteps of someone walking in the building next door. Electromagnetic compatibility is another relentless challenge. The powerful, oscillating electric fields inside the drive can induce stray currents in nearby spacecraft electronics, causing catastrophic interference with navigation or communication systems. Shielding is essential, but it is heavy, and every kilogram of shielding directly negates the mass savings the drive is supposed to provide. Scaling the thrust from a laboratory curiosity to a useful force introduces its own brutal physics. Doubling the thrust may require quadrupling the power input and the mass of the power system, quickly hitting a point of diminishing returns where the drive is too heavy to move itself, let alone a spacecraft. Reliability over decades is the final, towering hurdle. A satellite must operate flawlessly for 15 years with no possibility of repair. A single capacitor failure, a tiny crack from thermal cycling, or a layer of degraded superconductor would render the entire system useless, stranding a billion-dollar asset in orbit. This forces a critical safety question. How do we test and certify a technology so new that its failure modes are completely unknown? The answer demands a new engineering philosophy, one built on redundancy, fault tolerance, and ultimately, a humility that acknowledges we are building machines to sail on a sea whose currents we are only beginning to map. A silent engine carries a hidden roar of potential consequences. The immense energies required to warp space-time or manipulate quantum fields would not be gentle. An unstable warp field could theoretically rupture, releasing its stored energy in a catastrophic burst of gravitational waves, shaking apart any nearby structure. A malfunctioning quantum vacuum plasma thruster might not just fizzle out. It could collapse, potentially releasing a pulse of hard radiation or creating a temporary, unpredictable distortion in local space. The risks extend beyond the drive itself. Consider the power source, a compact fusion reactor, or even more perilously, an antimatter containment system represents a bomb waiting for a single point of failure. A breach in a magnetic bottle holding even a gram of antimatter would result in an annihilation event with the force of a small nuclear weapon, vaporizing the spacecraft and creating a lethal debris field in orbit. Safety engineering pioneer Dr. Nancy Leveson argues that for such unprecedented technologies, we cannot simply add safety features as an afterthought. Safety must be the foundational principle woven into the design from the very first sketch. This means building in multiple, independent layers of protection. A warp drive would need not one, but several redundant field stability monitors, each capable of initiating a safe shutdown sequence if a single parameter drifts outside its nominal range. The electrical systems powering a Mach Effect thruster would require fault-tolerant architectures where the failure of any one component is automatically compensated for by another, preventing a cascade into disaster. The ethical dimension of testing is immediate and profound. Could we ever justify a full power test of a warp drive in low Earth orbit? The potential for a miscalculation to affect the orbital paths of thousands of satellites, or even to subtly alter the local gravitational environment for crews on the International Space Station, is a risk no responsible agency would take. This forces a clear protocol. Initial high-energy testing must be conducted far from our planet, perhaps at a remote facility at a Lagrange point or on a dedicated trajectory into deep space. What about the exotic matter required for some concepts? If we ever learn to produce or stabilize negative energy densities, its containment becomes a paramount safety challenge. A leak of exotic matter could have completely unknown interactions with normal matter, potentially triggering unpredictable and irreversible reactions. The radiation profile of these systems is another critical unknown. The intense electromagnetic fields and high-frequency oscillations could generate novel forms of radiation, requiring shielding that does not yet exist. How do we protect a crew from a storm of particles we have never before encountered? These are not minor engineering puzzles. They are fundamental questions about our right to experiment with forces that could, if mishandled, have consequences on a planetary scale. Our ambition to become architects of spacetime carries with it a profound duty to ensure our first designs do not become our last mistakes. This careful balance between bold innovation and profound responsibility forces us to look beyond the immediate horizon toward the ultimate legacy these technologies could leave for all of humanity. Our survival as a species may ultimately depend on slipping the bonds of a single world. This is the long-term vision that transforms these engines from scientific curiosities into tools for species-wide destiny. Massless propulsion offers a plausible pathway to becoming an interstellar civilization, a goal championed by thinkers like Stephen Hawking, who argued that spreading beyond Earth is our best insurance against planetary catastrophes. The first milestone would be the generational ship, a self-contained world sailing for centuries. With constant, low-thrust drives, such a vessel could maintain a comfortable artificial gravity and steadily accelerate across the vast gulf between stars, its passengers living and dying in a journey that their remote descendants would complete. A more advanced possibility is rapid transit, where warp-driven craft could reach nearby exoplanets like Proxima Centauri b in a time frame of years, not millennia, turning these distant dots of light into tangible destinations for exploration and perhaps even colonization. The sociological impacts would be as profound as the technological leap. A crew on a centuries-long voyage would develop its own unique culture, language, and social structures, fundamentally diverging from the humanity they left behind. The very concept of home would be redefined, no longer a single planet but a fleet of arks or a network of scattered colonies. This expansion would be driven by the search for habitable worlds, a quest that propellantless drives make practical. Instead of simply observing exoplanets through telescopes, we could send swarms of probes to analyze their atmospheres, map their surfaces, and finally answer the ancient question of whether we are alone in the universe. The technological spin-offs from this endeavor could revolutionize life on Earth. Mastering the manipulation of gravity and space-time might lead to fundamentally new forms of energy generation, perhaps by tapping directly into quantum fluctuations. The materials science required to contain a warp bubble could yield substances with unimaginable strength and durability, transforming everything from construction to transportation. What does it mean for human identity if the stars become our backyard? We would transition from being a single-planet organism to a cosmic species, our stories and myths expanding to encompass the narratives of multiple worlds. This grand synthesis of every principle we have explored, from quantum sails to warp fields, points toward a single, unifying truth. The quest for gravity without fuel is not merely about building a better engine. It is about securing a future for humanity that is as endless and open as the universe itself. Every path we have explored, from the contentious hum of the EmDrive to the silent geometry of a warp bubble, converges on a single, powerful truth. The future of massless propulsion will not be unlocked by a single genius or a lone experiment. It demands a grand synthesis, a balanced dance between the unyielding rigor of science, the bold spirit of collaborative innovation, and the profound wisdom of thoughtful regulation. We have witnessed the cautionary tale of the EmDrive, a story that teaches us the immense difficulty of isolating a revolutionary signal from a storm of mundane noise. It is a lesson in humility, reminding us that our desire for a breakthrough must never outweigh our commitment to the truth. At the same time, the promise of warp metrics and quantum sails fuels our ambition, showing that the equations of our universe may contain hidden doorways to the stars. These are not competing narratives, they are two essential sides of the same coin. One demands we question everything, while the other inspires us to dream of what could be. The sustainability benefits alone justify this arduous pursuit. A shift from consumptive, polluting rockets to clean, electrical propulsion would transform our relationship with both Earth and the space around it, allowing us to explore without leaving a trail of debris and toxins in our wake. This is not a mere upgrade, it is a fundamental paradigm shift in how we interact with the cosmos. Progress will be incremental, built on a foundation of patient, validated steps. A micronewton of thrust measured in a deep space vacuum test is worth more than 1,000 media headlines about impossible engines. This journey also requires an informed and engaged public, people who understand that real science is a slow, collective climb, not a series of dramatic eureka moments. And because the power to reshape spacetime is too great for any one nation or corporation to wield alone, our path forward must be paved with global cooperation, establishing new rules for the road before we build the vehicles. So where does that leave each of us? This is not a spectator sport. We all have a role to play in this grand synthesis. Whether you are a student choosing a path in physics, a professional advocating for responsible funding, or simply a curious mind sharing these ideas with others, you are contributing to the ecosystem of discovery. The ultimate reward is not just a new engine, it is the expansion of human knowledge and the securing of our future among the stars. This collective endeavor, weaving together every thread we have followed, brings us to a final, poignant reflection on what it all means for the human story. The silent engine could redefine our very identity as a planetary species. This entire exploration, from the controversial hum of the EmDrive to the cosmic geometry of warp bubbles, reveals a truth far greater than a new propulsion system. We are not just chasing a better rocket, we are grappling with the fundamental laws of the cosmos, seeking to become architects of spacetime rather than its passengers. The quest for gravity without fuel pushes us to question everything we thought was possible, transforming space travel from a dirty, expensive endeavor into a sustainable and accessible journey. Arthur C. Clarke once observed that the only way of discovering the limits of the possible is to venture a little way past them into the impossible. That is precisely where we stand today, on that thrilling edge. Your curiosity is the most vital component in this grand experiment. Which of these concepts captures your imagination the most? Is it the elegant simplicity of surfing gravitational waves, or the profound mystery of a machine pushing against the quantum vacuum? Share your thoughts and join the conversation below. Subscribe to stay with us as we continue to investigate the technologies that will define our tomorrow. We are not merely watching this history unfold. Together, we are helping to write